When you feed a modern large language model hundreds of thousands of words and ask it to retrieve a single fact, the system physically breaks down. This is known as the needle in haystack test, and it exposes the exact hardware limits of current AI sequence architectures. This chart maps recall accuracy against increasing context lengths. Notice top-tier models like GPT-4 and Mamba 2, their accuracy collapses approaching 100,000 tokens. But the Titans architecture is an anomaly. It maintains near-perfect recall past the 1 million token threshold. Brute-forcing massive parameter counts into a standard model cannot solve this recall failure. Scaling past millions of tokens requires a strict mechanical departure from how sequence generation handles memory. Adding exponentially more compute power to a standard transformer architecture does not yield a proportional increase in its memory capacity. The engine driving these models is the self-attention mechanism, which calculates the exact relationships between different words in a sequence. For capturing direct dependencies within a highly restricted text window, the math is flawless. However, the computation required to calculate those relationships squares with every new token added to the sequence. When a model attempts to run self-attention across millions of historical tokens simultaneously, the arithmetic scales into numbers that modern hardware simply cannot process. To achieve a truly infinite context window, engineers must completely decouple the immediate processing of a sentence from the long-term archiving of a document's history. Treating the attention mechanism as a long-term storage vault is the exact reason standard models hit an insurmountable hardware wall. To see why that hardware wall exists, we have to look past the algorithmic theory and examine the physical layout of the graphics processing units running the computations. Modern GPUs are divided into two distinct zones. First, there is the high bandwidth memory, or HBM, which acts as a massive but slow-moving data pool. Connected to it is the SRAM, a tiny hyper-fast processing zone directly on the compute chip, where the actual math happens. Standard transformers suffer from a severe input-output penalty. To calculate attention for a new token, the GPU must constantly drag massive key and value tensors, the data matrices encoding the memory state of the attention layers, from the slow HBM pool over a narrow physical bridge to the fast SRAM. This starves the compute cores while they idle. Hardware-aware algorithms like flash attention mitigate this traffic jam. Flash attention splits the large attention matrices into smaller blocks, keeping the operations tiled entirely inside the SRAM zone without constantly returning to the HBM pool. By perfectly managing the physical movement of data, these optimizations maximize the hardware's efficiency. Yet they only delay the inevitable quadratic explosion of the underlying attention math. To bypass this quadratic penalty entirely, alternative linear architectures attempt to compress a document's entire history into a single, fixed-size cache of keys and values. The mechanical flaw with this linear design is its reliance on additive compression. When you continuously append new data vectors into a bounded mathematical space, the matrix inevitably fills up. The newest data simply forces the oldest information to spill over and vanish. This constant overwriting destroys the model's precision. If you ask the model to retrieve a localized fact buried deep in the sequence, the specific data points have already been compressed into noise by the sheer volume of newer text. Relying on an additive matrix to store information is a mathematical dead end. It cannot preserve the fidelity of longitudinal context. The Titan architecture abandons the monolithic processor. Instead, it redesigns the sequence model into a confederated cognitive system, separating tasks exactly the way human memory operates. The architecture splits the data pipeline into three distinct branches. The first is the core module. It utilizes the standard attention mechanism, but strictly as a highly precise, limited-window short-term memory to process discrete chunks of text. The second branch is the persistent memory module. This consists of learnable data and parameters that act as permanent storage for the overarching rules and structural knowledge about the specific task at hand. The breakthrough is the third branch, the long-term neural memory. This deep neural network structure sits completely separated from the short-term attention block. It archives history not by adding vectors to a cache, but by actively learning the data at test time. Isolating these three functions allows the Titan model to calculate the immediate context perfectly, while simultaneously maintaining a boundless, highly compressed historical archive running offline. This neural long-term memory operates as an online meta-model. Unlike standard architectures whose weights are frozen after initial training, this module dynamically updates its own neural weights during inference as it reads new text. The system decides exactly what to memorize using a mathematical trigger called the surprise metric. This is calculated using the gradient, a measurement of how much a network needs to adjust its internal weights to account for new information regarding the incoming token. If a token is highly anomalous, it produces a massive gradient spike. This spike physically alters the parameters of the network's nodes, directly hard-coding the abstraction of that surprising event into the model's permanent structure. To prevent the neural network from overwriting itself entirely, the module uses an adaptive weight decay mechanism. This acts as a continuous fading process, slowly dimming the least accessed memory paths so the network maintains optimal capacity for new abstractions. By utilizing gradients instead of simply concatenating matrices, the Titan architecture transforms historical storage from a passive, overflowing cache into an active, self-optimizing neural network. In practice, these three modules synchronize to generate sequences without triggering the standard hardware bottlenecks. We see this mechanical flow clearly in the model's memory as a context, or MAC, variant. When a massive context sequence enters the system, the model immediately divides the text into fixed, manageable temporal segments. The current segment pings the long-term neural memory, returning a compressed historical abstraction vector, HT. The system physically concatenates this vector, the persistent parameters, and the text segment into a single sequence before entering the short-term attention block. This sequence-building method guarantees the attention mechanism operates with flawless, localized accuracy while remaining fully informed by the deep historical context of the entire multi-million token dataset. Offloading this historical data into test-time updated neural network parameters solves the memory bandwidth problem outright for the system. The GPU completely bypasses the requirement to reload massive key and value sequences from the slow HPM pool back to the fast SRAM chip. Looking back at the recall benchmark chart, the results are clear. This exact parameter offloading technique is directly responsible for the Titan architecture maintaining elevated, stable accuracy as the sequence length approaches its maximum limits. Decoupling short-term attention from neural long-term memory allows the system to process infinite context windows without shattering hardware constraints. True scalability requires moving past a single processor and mimicking the cognitive confederation of human memory.